Okay, differential equations. We've got three vectors, x1, x2, x3. You can see them up the top there. Take a minute to read them. Okay, so the first part is we've got to write x as a linear combination of the three vectors using the superposition principle. So we can see column vectors there. X2 can also be written as 0 e to the t 0 by multiplying through the matrix. And therefore we just write, this is part one, nice and simple. A linear combination indicates that you've got the three vectors multiplied by coefficients c1, c2, c3 used to create the linear combination for the vector x. But now we've got to determine whether these vectors form a fundamental set of the solutions in the second part. So what is a fundamental set? It's any set x1, x2, up to xn of linearly independent solution vectors. So linearly independent means that there exists a set of constants c1, c2, all the way up to ck, not all equal to 0, which mean that the linear combination x goes to 0 with those constants. So we're looking for a non-trivial solution here. So how do we know if that's going to do that? We calculate the Wronskian. So set up the Wronskian, looks like this. We put the x1 down the first column, x2 down the second column, and x3 down the third column, and calculate the determinant. We can do some little fancy tricks here, like the Becklin method, where we go whoop, 3 one way, take the sum, write down the next two columns, go the other way, or I don't really get the one that Professor Kolesnik was talking about in class, which does that little star thing. It confuses me, but whatever suits you. I'm going to do cofactor expansion for this one. So we first look at this one, this entrance in the position 1, 1 in the matrix, pull it out the front, and then we get rid of those, the column that's in and the row that's in, and then we calculate the 2 by 2 determinant. This 2 by 2 determinant here, we'll just write that down for the second. The second one, we move across the top row. There's a 0 in the second spot on the top row. So we know that whatever's determinant we get for that 2 by 2 matrix will be multiplied by 0 and ultimately equals 0. So we can just cancel that out, as I've done right here. And finally, sine of t for the third one, we get the following. We take everything out of the top row and everything out of the third column and compute this 2 by 2 matrix here. So if anyone doesn't already remember, just the simple formula for calculating the determinant of a 2 by 2 matrix is the quantity in A multiplied by the quantity in D minus the quantity in C times the quantity in B. So for the first one we get cosine cosine multiplied by this times, cosine out the front from cofactor expansion multiplied by this times this, minus, this is 0 times all of this stuff, so that just goes to 0. And then we've got sine, this whole determinant is 0. So we calculate this one over here. There is another thing there. I might scroll up a minute. Can't, never mind. So A times D is this stuff times 0, that's 0, minus this stuff times E, that is E to the T there. So we get for this third part, negative cosine T minus sine T, all multiplied by E to the T. Simplifying, final stage is here. Cosine of T multiplied by, we just multiply E to the T throughout the brackets, and we do the same thing on this side. And then if we multiply cosine t through both terms here and sine t through both terms here, we get this lovely line of nonsense. But it's not nonsense because we can take out a factor of e to the t. And then what do we get? We get e to the t, get negative cosine t, sine of t plus cosine squared t plus cosine t sine t plus sine squared t. If the negative cosine t sine t will cancel out with a positive cosine t sine t, so we get e to the t multiplied by sine squared t plus cosine squared t. But that is just equal to 1. So overall, the determinant of this Wronskian of x1, x2, x3 is e to the t. And what do we know about things raised to the power of, like, the number raised to the power of anything? It's never 0. Well, it's never negative either. It's always greater than or equal to 0, which implies that the Wronskian for all values of t is greater than 0. And that means it forms this fundamental set because the Wronskian is not 0 for all t. So we're happy, as indicated by the smiley face right here. Therefore, we can write our closing sentence. The general solution of the homogeneous system on the interval is a linear combination of the vectors given in part 1. Thank you for watching.